Thank you so much. It's such an great. It's such an honor to be here at this fantastic conference. Let's get started. We saw this picture already. Dinesh sent this to me, but I just want to take you back. This was 2007. I think it was at an Arizona winter school. And at the time, I was finishing up my PhD, and my job situation was sort of up in the air. And I was thinking about maybe I was going to leave math, maybe go to Wall Street. I was already interviewing and all that. So I had a big decision to make, but I really thought about it, and I looked at this picture a lot, and I was like, you know what, I'm not done. I'm not done. And I sent my family was like, why don't you come back to New York and work for Wall Street? It's going to be great. And I sent them an email, and I attached this picture with a long and flowery explanation. I just looked at it. It's like really mushy. But anyway, I explained like how we talk about our advisor as kind of our parent, and how we have like mathematical descendants and all that, and how we're like a big mathematical family, and it all just kind of clicked for me. So I think of this as one fantastic community, and if you think that that is something worth fighting for, worth something leaving to our descendants, our mathematical descendants, then I hope you will join that fight with me. All right. So let's get started with our talk. I kind of thought about, when someone asked me, what do you do for your research, someone who's not a mathematician, I said, well, I study like crazy p-adic clouds of dust. They're super interesting, and they look like this, and that usually shuts the conversation down pretty quickly. But I thought it would be like a good metaphor for this talk. So it's sort of a good visualization of what a Berkovich space looks like. You have to kind of add a lot more limbs to this tree, but it's also a good metaphor for how this talk is going to go, because I think of Tate's contributions as sort of central to this, and to plan a talk like this, I kind of have to choose a path through this tree and then find a way to the boundary somehow. So I'm kind of doing this. So that's how I arrange this talk. So the first, so the non-Archimedean geometry portion of this talk is going to be background material. You can think of it as a sequel to Brian's talk the other day, who talked about what rigid analytic spaces are. My motivation, though, is going to be a very familiar fact from the theory of Riemann surfaces. So let's say we're over the complex numbers, and we have a compact Riemann surface of genus G. So you consider its universal cover. That's also going to be a complex manifold. It'll be simply connected, and there's a theorem that there's only three of those. There's the Riemann sphere, the complex plane, and then the upper half plane. So there's this trichotomy depending on whether the genus is 0, 1, or greater than 1. Right? Very famous fact. It kind of informs the whole geometry of curves and Riemann surfaces. This upper half plane, sure, it's all the complex numbers with positive imaginary part. It's also the unit disk in the complex plane. Hold that thought. So what else do we know about this situation? Well, basically, curves which are hyperbolic, they have hygenus, they're always uniformized by the upper half plane. So you can always express them as the upper half plane modulo a group of automorphisms. The automorphism group of the upper half plane is this group, PGL2R. And, PSL2, okay. Sometimes I confuse the upper half plane with both the upper and lower copies together. Anyway, when gamma is a subgroup of this, H mod gamma is going to be a Riemann surface. If you choose gamma to be a subgroup coming from arithmetic, like maybe it's a congruent subgroup of SL2Z, then you know what you get. You get a modular curve, and in general, you get a Shimura curve. And those are really relevant to the Langlands program. All right. So my question from this slide is, do these statements have any analog when the complex numbers are replaced with a non-Archimedean field like QP? That's going to be our motivation. What happens to this theorem? All right. So, all right, certainly in the material on this slide occurs to anyone who has studied p-adic anything, but we're going to go over it anyway. So let's say K is a non-Archimedean field. So that means a complete field with respect to a non-Archimedean norm, right? So the norm doesn't satisfy it satisfies a version of the triangle inequality that's stronger. But it could be characteristic 0, or it could be characteristic P. It could be, for instance, a field of Laurent series over any field that you want. But QP is a good example. So if you want to do geometry over K, the thing that might occur to you, and it occurred to Serre, is that you can define something that's like a K manifold by saying, okay, it's going to be a topological space with a sheaf of functions. The topological space, it should be covered by balls, like opens, which are isomorphic to like this thing, OK to the n, right? So that'll be like compact opens. And maybe the sheaf of functions on this is analytic functions and n variables that converge everywhere. All right. So that's a reasonable thing to do. You could even go as far as to define k analytic spaces. So just maybe like that's vanishing loci of some system of analytic functions in such a ball. So you can try to just copy the theory that you might do to create complex analytic spaces. All right, the main issue, such spaces are going to be totally disconnected. So that means that interesting global phenomena are going to be impossible to study because your space always just breaks up and breaks up and breaks up some more. So there's going to be no hope of doing the things from the previous page so well, at least not this way. And you can trace that trouble to the fact that OK itself is totally disconnected. And for instance, it's separated, it's disconnected by these two sets, everything less than 1 and everything equal to 1. Let's just pause for a second to notice that these two are actually open. This is open because the absolute value is continuous, right? But this one is open. It's not open in the usual kind of topology on the real numbers, right? But it is here. Wait, what did someone say about Dwyer calling this like a tire? I can't remember. The unit tire. Yeah, so this is called the unit tire in non-Archimedean geometry. It's thick. And let's just go over the reason why. If you have absolute value 1, then as soon as you add something of absolute value less than 1, the absolute value is just going to be 1 here. So adding something in this open ball keeps you inside of this unit tire. So this tire has to be open because it's translated.
The great term is annulus.
Versus tire? I know tire is not the technical term. But OK, I know. But I mean, is there one correct term from this? I've talked to so many people about p-adic geometry, and they say it's the unit circle, or it's an annulus, or it's a tire, and I wouldn't go far as to say there's only one correct term. Right, you want to, I just think this conversation reflects a certain, like a certain failure of our visual cues about how p-adic geometry works, because we're in the real world, aren't we? So we're trying to describe something with only one radius. As Noam says, there's an inner radius and an outer radius, but they're the same. So is it a circle? Circle seems like it doesn't have any thickness. So the fact that we're having this conversation means p-adic geometry is kind of interesting. It's kind of hard. Yeah, what? I'm going to use tire. OK. All right. All right. So as I said, the problem with K-manifolds, this thing is totally disconnected. So p-adic geometry has to solve, or non-Archimedean geometry has to solve the problem of how to connect it. And Tate did this. So Tate's theory of rigid analytic spaces solves this problem of connectedness, throwing away the naive topology on OK to the n. This has a metric on it, and we just use that to make a topology. With instead a G topology or a Grothendieck topology, you decide which opens are allowed, which are admissible, and you also decide which coverings by admissible opens are admissible coverings. So you have to keep track of what all of these admissibility notions mean. And that means you're able to just kind of keep the underlying point set, but change the topology and get the theory to work from there, which for many purposes works out really, really well, and the theory has a lot of successes. Tate's theory inspired some modern variants, which solve the problem a different way. And so it's kind of a trade-off. So the variants I'm talking about are Berkovich spaces and Huber spaces. Adic spaces, they're called. And the trade-off is, OK, we're going to forget about this G topology. I want an actual topology with actual open sets, none of this categorical stuff. But in exchange, I have to add a ton more points to this set, OK to the n. So that's the trade-off you make. Today, we're going to mostly talk about this world of adic spaces because, well, a lot of the literature, especially that coming from Schultz's perfectoid spaces, kind of starts from there. And adic spaces is a really broad category that includes rigid analytic spaces and also formal schemes, and allows you to kind of go from here to here. You can take an adic generic fiber. We're going to go over all of that. So OK. All right, so this is a review of what the points in the adic space are. So I'm going to start with an example of a Banach algebra. And so K here is going to be our non-Archimedean field, like QP. A good example of this is the Tate algebra. So that's K. I write it angle brackets T. But the notation sometimes is the brace. I think that was what it was in Brian's talk. So that's defined as the completion of the polynomial algebra with respect to the sup norm. So you can also think of it as power series in T, where the coefficients go to 0. For such a ring, we have this notion of a continuous valuation, and these are going to form the points in the adic space. So this is going to be a map. I write it this way, f to absolute value of f. The absolute value is the thing that is changing throughout the space. So it's going to go from A to the elements of some totally ordered abelian group, union 0. So it's allowed to, so this gamma here is written multiplicatively. For now, you can think of it as positive real numbers. You're also going to allow 0 as a possibility, and indeed, this axiom says that the absolute value of 0 should be 0. We also have 1 should have absolute value 1. It's multiplicative, and also this has this kind of non-Archimedean triangle inequality. All right. The fifth condition is something to do with the topology on A. The valuation is supposed to be continuous in the sense that if you pick a G as your upper bound, the kind of open ball bounded by the valuation of G is supposed to be open. So with these 5 axioms, we have a notion of a continuous valuation. This is supposed to be one of the points in the adic space. In algebraic geometry, we have schemes, and each point has a residue field. And it's similar here. Each time you have a valuation, what you can do is kind of, oh, there's going to be a kernel of the valuations. Other elements might go to 0. That's going to be a prime ideal of the ring. Mod out by that prime ideal, and take the fraction field, and complete. And you get this new field L. And this L is going to be a complete valued field. And that's the residue field of this absolute value. All right, given A, I'm going to let SPAA, so this is Huber's notation. The adic spectrum is the set of continuous valuations on A up to some evident notion of equivalence between valuations. So this is this set. The set's going to have a topology, okay? So the topology takes some getting used to. In usual algebraic geometry, it's sort of like this condition. The non-vanishing of elements gives you a standard open. But we also want to allow for inequalities to give us open subsets. So the general thing to say is you have an F and a G, and you give this the topology generated by such inequalities, where you have a kind of non-zero G, and every absolute value giving F something bounded by G is going to be the opens. And you can also put a structure pre-sheaf on this topological space by defining OX of U, if this is the U, to be some sort of completion of A adjoin F over G. Well, you'd also have to, I should have written this. You also should invert G in this. G should be invertible in this. So you kind of, it's a multi-step process. You adjoin F over G, and then you complete, and then you invert G there. All right, so the topological space, at least, I can tell you some things about it. In the case of this Banach algebra, K angle brackets T, the Tate algebra, one thing is that it contains a point for every element in OK. Because each time you have an element of OK, you have this kind of substitution homomorphism. And then you're in K, so you can just take the K absolute value here. So that gives you a continuous valuation. So K contains a point for everything in OK. But it contains many more points, and actually it's connected. So this solves the problem of connectedness, because it takes OK, it adds more points, and the resulting space is actually connected. It contains many, many, many more points. And in fact, I could say something like this. Something in this story is path connected. So X is a spectral space. That's one of the features of working with adic spaces rather than Berkovich ones. It's quasi-compact. Spectral means that it's isomorphic to the spectrum of a ring. So it kind of behaves like algebraic geometry in that there might be points which specialize to other points, like generic points. It has that quality. It's not Hausdorff. its Hausdorff quotient is the Berkovich spectrum. This is what's studied in Berkovich theory, and then that Berkovich spectrum is actually path connected. It looks more like the picture I showed you at the beginning, where you have this tree, although it branches an awful lot. All right. Oh yeah, so I wanted to give a brief justification for the claim of connectedness. Like, why does this actually solve the problem? So let's, so I'm kind of going to propose disconnecting the set like I did before with QP. So on the one, I want to decompose X into two sets U and V. And one of them is going to be the tire. T is equal to 1, right? And the other one is going to be sort of t is less than 1, but I want something open. And I told you what the open sets are. They're defined by such inequalities. And pi here has sort of absolute value greater than 0, so it's going to be not equal to 0. So all of these are of the allowable sort. And if I take the union of all of them, that's going to also be open. And it sure seems like this inequality is like, OK, t is less or equal to pi to the 1 over n. If pi is in this range, it seems like I'm going to union up and get up everything less than 1. So this sure seems like it's everything that's where t is less than 1, right? So doesn't this disconnect x? No, it doesn't disconnect x, because the union of u and v is missing a point. I have to tell you which point that is. It involves a higher rank valuation. So there's a continuous valuation on this ring. The group of it is a product of two groups. Maybe you give it the lexicographical ordering somehow. So this is the kind of dominant one, and then this is the secondary one. So this is self-explanatory. This gamma here is just some element that's defined to be infinitesimally smaller than 1. So it's less than 1, but it's bigger than every real number that's less than 1. So it kind of goes in between. The absolute value should just be gamma. Thank you. That was silly. OK, thanks. All right, so there actually, I'm claiming to you there is a continuous valuation that thinks that t is ever so slightly smaller than 1, but it's bigger than every root of pi. So it's bigger than every real number in the interval 0, 1. OK, so this u and v, together it's still missing this point. So the existence of this point is really important for having a theory where you get connected spaces. Okay. So in this story, you could have also played the same game where gamma is a little larger than 1. And that's a little bit of a problem for the theory as I've stated it. It's kind of best to exclude this. So if I want this to be associated with a closed disk of radius 1, it shouldn't include points that are larger than 1 in absolute value. So the theory should really exclude such points. And there is a workaround for this that Huber invented. Instead of just working with the ring here, you carry around this integral subring, and you say all of my absolute values have to satisfy this condition. So if t belongs to this subring, then t should be less than or equal to 1. So the set SPA A with this additional condition is called SPA AA+. But on the first reading of this, you can always ignore the A+. Don't just basically not worry about it. Any questions so far? Yeah?
You mentioned that also the Berkovich space is path connected.
Yeah.
The space doesn't include high rank valuation. Yeah. So you should expect to see also like a valuation of rank 1. Wouldn't appear in this union, right?
Oh, so the valuation of rank 1 does appear in this union. OK, so the question was like, the Berkovich space is, OK, so the Berkovich space is a little bit different in that it is missing those higher rank points, but it does still have the kind of Gauss points. So that's going to be contained in here because the Gauss point thinks that this is. But the thing is, you can, in that situation, OK, the topology is defined a little bit differently there. You kind of have the Gauss points for various radii, and this is something that Brian discussed, and that's how you connect all the way up to this point.
The point is V is not open.
Yeah, in that situation, the V is, yeah, the V is not open in Berkovich space there. Yeah, OK, that's right, that's right, that's right. Yeah, so there's slightly just kind of different topologies. Yeah, the adic space world, it really resembles the scheme world a little bit more in that, well, yeah, well, yeah, put it that way. OK, so what is an adic space? So we just constructed out of an A, like a a Banach K-algebra, together with this auxiliary subring. We constructed a topological space with a pre-sheaf of rings. We can go a little bit further than this. The ring A doesn't have to be a Banach K-algebra, and that's a really great positive for the theory because it includes lots of other things. The theory has A being a certain kind of topological ring called a Huber ring. So the condition for being Huber is this. There's an open subring, and the open subring carries the topology generated by some ideal I, which is finitely generated. And this is what's necessary to get the theory off the ground. We can check that the Banach algebra, like the Tate algebra, for instance, is like this. Well, I can explain this in just a second. Oh, no, I don't do it on this page. If A really was the Tate algebra, then this can be the integral Tate algebra. And that topology is generated by any element of absolute value less than 1 inside of K. So it does satisfy this criterion. Here's the definition. An adic space is a space X equipped with the sheaf of topological rings OX, which is locally this. So it's sort of like how you build schemes out of affine schemes. We build adic spaces out of affinoid adic spaces, which look like this. And it's a very big category, so it contains formal schemes. And there's a fully faithful functor from such to adic spaces. If you have an affine formal scheme, so it's SPF of A0. So A0 is a ring with an I-adic topology. And let's just assume that ideal is finitely generated. So then the A0 can serve kind of in both spots over here. So in that circumstance, you actually get a perfectly good adic space out of this. And the A0, it doesn't even need to have a topology. It can be discrete. It can be Z. And so SPA ZZ is a perfectly good adic space. So this is something that kind of can't be done in the rigid world, for instance. There's no category, kind of obviously speaking, that contains, in Tate's formalism that does this. Rigid analytic spaces also enter into adic spaces. So in Tate's theory, you have certain Banach algebras A, and you consider their max spec. I guess sometimes it's just called SP, but it means all of the maximal ideals. And this affinoid rigid space gets just sent to SPA of A circ. Okay, so A circ is all the power-bounded elements of A. For A, a quotient of the Tate K algebra. All right, great. So that's just a certain kinds of A go into this. And then finally, and this is kind of key, adic spaces contain some other funny-looking spaces. I'm calling them oddballs here. So S here can be some profinite set. So it's a topological space. It's like an inverse limit of finite sets, okay? And I can make the ring of continuous functions from S to K. And this is going to be, again, a Banach algebra like this A was. We're under the subnorm. And you can make an adic space out of that. And I'm going to just call that S underline. And it's like the constant adic space corresponding to S. And the underlying topological space of S underline is just S. So there's A naught would be C of S comma OK. Yeah, so it's like bounded. Functions bounded by 1 would serve the role of the A plus in that situation. Okay. So adic spaces contain lots of other things. Okay, so what kind of, I guess, sealed the deal for me that I should really study these things seriously is that there's this notion of passage to the generic fiber, which is like kind of technical in the rigid, I mean, Brian talked about this kind of passage due to Raynaud in certain circumstances. So the way that it works in adic spaces is sort of literal in the sense. So the generic fiber is just the fiber over a generic point, which has a certain appeal to me. So first of all, I'll tell you what SPA ZP is. It consists of just 2 points, an eta and an S. As you might expect it would, it's the same as spec ZP. The valuation eta thinks that P is between less than 1, and the valuation S, the special point, thinks that P is just 0, right? So we can form this formal disks, so this is going to be basically like a formal scheme, but the adic version. So it's SPA ZP double brackets this. So think of this, what this would be if this was an F, SPF, then it would just be open prime ideals in here, but there's just one, the maximal ideal, so it would just be 1 point. But the adic version of this has tons and tons of points, in fact, uncountably many, as long as D is positive. So this I'll call the adic formal disk, and it's fibered over SPA ZP, right? And it's got a generic fiber, and the generic fiber, okay, I mean, sure, formally I can write it this way, it's like a base change, but really all I'm doing is saying I want all the points that map to this point. And that's going to be just an open subset of the full DD. So it's just the open subset of valuations that think P is not 0. So this kind of passage is really like easy. It's literal, I would say. And then what sort of space is this? So first of all, unlike in the theory of schemes, if you have kind of affine and affine and you cross them together, that should be affine, right? Not so here, and that takes some getting used to. So this DD eta, it is not an affinoid. It's not even quasi-compact. So that is unusual if you're coming from algebraic geometry. So it's, and I can try to convince you of this non-compactness by saying something like, okay, here's a rational open of DD formed by this inequality. Here's P and here's Ti to the power n. And I mean for all Ti, so I guess it's an intersection of finally many such opens. So these exhaust the whole space. If P is not equal to 0, then since the Ti's are topologically nilpotent in here, some power of them eventually, the powers of them have to go to 0, so they're eventually going to be less than or equal to this thing. So that's why all of these spaces exhaust everything, but no finite collection of them covers the whole space. So the thing is just literally not quasi-compact. Yeah. Sure, it's a Stein space, yeah. Yeah. So I mean, yeah, the theory is pretty well developed. So it's not affinoid, but it is Stein. So if you know what that means, then it should have some properties of affinoid spaces. But, yeah. All right, well, are there any, since this is a natural question point, are there any? All right, great. We're all adic experts now. And now we can return to the original motivation for the talk, which was these uniformization theorems. Do we have them? What about curves over QP? Okay. So fortunately, Brian did some of my work for me and already told you about the Tate curve. So let's just repeat this theorem. Let's suppose you have an elliptic curve over K. And K, by the way, it can be any non-Archimedean field. It doesn't have to be a QP or anything p-adic. Okay. I assume that it has split multiplicative reduction. Then there's an element Q in K star less than 1, and an isomorphism of rigid spaces. So GM, I mean the rigid version of that, mod Q to the Z onto E analytic. So there's a way to turn E into the rigid space, and this is going to be an isomorphism. All right. So this could be considered something like a uniformization theorem. So Tate's formula, since we heard a lot about them, I just wanted to have this coda to that discussion. There is an adic space lying over SPA Z double brackets Q. In fact, we already know there is, since Brian told us about it, there's already a formal scheme over this base. So you can consider it just as an adic space now. And you can restrict the Q not equal to 0 locus in this adic space. And then you get an elliptic curve. Then you get the analytic version of an elliptic curve that lives over here. So you can kind of do the constructions Brian was talking about at all of the primes at once. All right. So the question I want to discuss right now is there a generalization of this phenomenon? Like, if I take any elliptic curve or even any curve, might there be some universal cover? Who knows what it looks like? But can you express the curve as a quotient of some space, some standard space? And the answer is not completely. So it's, with wisdom you develop like, okay, some things can be repeated from the complex world, but some phenomena are truly p-adic. And I would say that one truly p-adic phenomenon is good reduction. There's just no notion of this in the complex world. And when you have an elliptic curve with good reduction, there just isn't a similar uniformization. Not like this. All right, so what is there? All right, there's a delightful story of Mumford curves that I want to share with you. Okay, so first, Tate's curve is nodal. So it's, its special fiber is like P1 glued to itself at one point. And when your curve has this sort of reduction, then there actually is a good uniformization. So the definition that's relevant here is that of a Mumford curve over K. So this means that there's a model for it. There's a flat formal scheme over OK. The generic fiber is supposed to be what you started with. And the special fiber is a configuration of P1s, of projective lines, that meet with only split nodes as singularities. So singularities are allowed, but the only kind that's allowed is sort of locally looks like two axes crossing, and the slopes of those axes should be rational. So Mumford's theorem, so it lives in the world of rigid geometry, and there's also a complex version of it. If you have a certain kind of subgroup of PGL2K called a Schottky group, okay, so what's that? So it's a discrete subgroup of this group consisting only of hyperbolic elements. What does that mean? Okay, the elements in question, their eigenvalues should have distinct absolute values. That's what a Schottky group is, and this theorem gives you a recipe for constructing curves. You take P1, and you remove from it the part where gamma kind of has like limit points. So you remove exactly the locus where the group gamma acts discontinuously, so that you would hope that the quotient is actually going to be a curve. So after removing those bad points, that bad locus, the quotient is going to be the rigid version of a Mumford curve X. The genus of that curve is G. G is the number of generators of gamma. So that's really cool. So this is a way of constructing Mumford curves, and conversely, every Mumford curve appears this way. So as long as you have this kind of reduction, where it's just rational curves, then there is a uniformization. It's a uniformization by some open subset of P1. And that's really interesting because in the complex case, everything was a subset of P1 also. It was either all of P1, or it was P1 minus 1 point, or it was P1 minus, or just 1/2 of P1, I guess. That's the other point. In the setting of the Tate curve, what's this gamma, this Schottky group? Well, it's just got one generator, and here it is. So that's acting by multiplication by Q on the complex plane. That has two limit points, right? The origin and infinity. You have to throw those out to get GM, and then GM is the thing that does the uniformization. Yeah, interesting. I couldn't write, it's hard to write down other Schottky groups, as you might imagine, just generators. So the story continues with some examples of this kind of uniformization of Mumford curves. And right, so this was just too interesting not to discuss, but I'll try to do it quickly. If I have an indefinite quaternion algebra ramified at P, then there's a way to pass from there to some Shimura varieties. In this case, they're Shimura curves. You get one for each open compact subgroup of the adelic group of B. Oh, that should be B star. There's a typo. So the complex points are like H mod gamma, where gamma is going to be a congruent subgroup of B of Q. So that's like the theory of Shimura curves tells you this. It's interesting, so these are all curves defined over number fields, and it's interesting to ask like about their reduction mod P. In the special case where the level structure is really nice, like it's maximal at P, then you get a Mumford curve at P. So the analytic version of this thing is a Mumford curve. So you can ask, what is the corresponding Schottky group? And the answer is shocking. So, I mean, is it not? Here's the procedure for it. You take the quaternion algebra. So I said it was indefinite. So it's not ramified in infinity, but it is ramified at P. B bar, you switch the two. So it's ramified, it is ramified at P, but not, sorry, it is ramified at infinity, but not at P. So such a B bar does exist. The QP points of it should just be a matrix group, so the unit group there is going to be GL2QP, and that knows how to act on project the P1. Yeah. So I'm getting towards the theorem of Cherednik-Drinfeld here. And it says that this Shimura curve, considered as a p-adic rigid analytic space, you can make a uniformization of it. So I'm omitting some details here, but the short of it is that it's a union of quotients of HP. So what's HP? So now we're introducing HP. So this is the p-adic analog of the upper half plane. The upper half plane, you have to think of it this way. It's the Riemann sphere take away the real points of P1. And if I plug in QP instead of R, I get this thing. P1 over the QP, take away the rational points, P1, QP. So we have to omit kind of profinitely many points to achieve this thing. So this is like the Drinfeld's upper half plane, although it has been pointed out many times, it is not half of anything, and it is certainly not upper. There's no distinction between plus minus in this world. So, okay. All right, so I think this is truly amazing. And the gamma here is going to belong to this other quaternion algebra. And lest you think this is some kind of novelty, this theorem has a really important application. I would say the theorem was used to great effect by Ribbit in his proof of the level lowering theorem about modular forms. So this was really a key step. And that theorem played a key role in the proof of Fermat's last theorem. So, all right. Questions on that? I think we're in a new section now. Oh, yeah.
Maybe this is a question for afterwards, but I'm just wondering, what happens if you do this? Like, for the elliptic curves, you did it over Z power series cube.
Ah.
What happens if you do the same thing, like over the boundary of modular space?
Oh, you mean unite?
And what is gamma then?
Do you mean like unite everything over all primes?
Yeah, I mean, you just need something with like totally degenerate reduction, right? So,
Yeah.
So over Z brackets Q, this works for elliptic curves.
Yeah.
But you can, this probably, the same thing probably works over the boundary of, or maybe not over the whole boundary, but like in the neighborhood of a totally degenerate point.
Oh, okay, so you start with MG.
But then I'm just wondering what gamma is.
Oh, I see, I see.
In your example, it was still Z for the Tate curve.
I see. I think these questions have answers, but I do not know them. So you're asking about just higher genus curves and what the version of the Tate curve is. Yeah. Okay. Okay. So, all right. We're in the kind of third part. Yeah, the really interesting stuff is all at the end, so I kind of want to hustle a little bit. So, all of this is wonderful. I just want to point out some weird stuff about p-adic geometry, which just doesn't have any complex analog at all. And so it's kind of a it's inviting at the same time that it sort of warns you away from it. So p-adic geometry and complex geometry sounds like we've put them on an equal footing. We can study certain ringed spaces and yeah. But there's real differences, and I want to highlight a couple of them. And lest you think that the differences have to do with arithmetic, I just want to work over an algebraically closed field. So this C is supposed to be like an analog of QP. Algebraically closed value field containing QP. So this time, we're not using a general non-Archimedean field. Now it's p-adic geometry. So our fields will contain QP. P is going to generate the topology on everything now. Big issue. It did come up in Brian's talk also. Smooth rigid spaces, they're not locally contractible. And this is so frustrating. So, when we think about manifolds, when you look up at them real close, they're made of balls, and balls are obviously contractible. But in the p-adic world, these balls, they're not even simply connected. And it doesn't matter how small you make the neighborhood, they'll never be simply connected. And I want to convince you of this. So here's the closed unit ball. I can find a bunch of finite Atoll covers that are not split. And here's one. So I'm going to add a new variable. And this is like a kind of Artin-Schreier equation. And so I was trying to work this out, like what the right convenient example would be. So this is what I came up with. But if you do the calculate, you can take the derivative of this polynomial and see that it's just not zero anywhere on this cover. So this is actually Atoll. And then another issue, which I'm not really going to go into, is that if you want to do calculus to this situation, if you want to do differential geometry somehow, then you might want to integrate a differential form one day. And too bad, you can't do it. So differential form's not even locally integrable. So here's dt over t. and you try to integrate it, sure, you get log. And that series has some denominators in it that make it not want to converge. And in particular, it's just never going to converge in any neighborhood of the Gauss point here. So if you want to set up a theory of differential forms, maybe you want to write down a Poincare series or Poincare sequence, but you'll find it's not exact if you set it up in the naive way, because closed forms are not even locally exact. Okay. All right, so what do we do about the situation? Well, so many of these issues are addressed really well, but it's very technical, and you have to kind of be a master of Schulz's theory of perfectoid spaces. But I want to just let you know, without going into the meat of this theory, that we have like really satisfying answers to these questions. So what is a perfectoid space? So it's a kind of adic space. Locally, it looks like an aphanoid. The A is supposed to be a perfectoid algebra. What kind of algebra is it? Well, it's got this property. All elements of A plus emit approximate pth roots. You can always take a pth root mod p, basically. And that condition usually means A is non-Noetherian. So basically, in every non-trivial example, the ring A is enormous. So that's a cost of working in this world. But I want to convince you that this condition of approximate pth roots really is the right one. I opened this with my first slide had something to do with like universal covers on it. So imagine trying to form a universal cover for something like this. You would take a limit over all kind of finite étale covers like this. And in that limit, you imagine taking the union of all of these rings, n varies. T here, modulo p, ends up being a pth power when you do it. And it ends up being a pth power kind of arbitrarily. So if you want to think about what a simply connected space could look like p-adically, it kind of has to be enormous like this. So once you realize that, it's sort of scary. You're like at the precipice. And you're like, if I really want to talk about p-adic geometry, I want to know what the kind of atoms in this theory are. What are the spaces of which everything else is glued, and they're enormous? So this page is just about philosophy. I've got 15 minutes left, so let's see if I can do it sort of fast. So as I said, the universal cover ends up being perfectoid. That's one feature. There's a notion of a topology that's beyond the analytic topology. It's beyond the étale topology. It's called the pro-étale topology, where you allow for certain infinite covers, infinite to one covers. And you can make a cover of X which is contractible in a certain sense that any étale cover is split. So I'm talking about Schulz's theory of like, it's in his book on étale cohomology of diamonds, but there's certain kind of totally disconnected perfectoid spaces which have this property. Another quirk of this theory is that characteristics are fluid. You can move between characteristic 0 and p through this kind of tilting process, and then that gives you access to Fontaine's period rings, and that's kind of how you do calculus in this world. And then another feature, all right, so if X is aphanoid, you can talk about the coherent cohomology of the structure sheaf. If I didn't put this plus here, it would just be, that would be acyclic, because these things work like schemes do. But when I put the plus there and just talk about the integral functions, that's almost 0. And this acyclicity thing, well, the case of a point's due to Tate in this p-divisible groups paper. So if X is a perfectoid field, this is a fact about Galois cohomology that appears in that paper. So Tate kind of sowed the seeds of this kind of thing. No, so it's almost in the technical sense. So almost 0 means killed by any element in the maximal ideal of OK. Yeah. So, oh gosh. OK, so it's in kind of the Schultzian philosophy. Sure, you have rigid spaces which maybe you very much want to study. But you want to study them by saying, OK, they're glued out of simpler pieces. Those simpler pieces are maybe contractible perfectoid spaces. They're really weird, they're not Noetherian, but kind of all you have to do is keep track of them and the way that they're glued together. So if you follow that to its logical conclusion, you arrive at Schulz's theory of V-stacks. So what does that mean? In a nutshell, we're talking about a sheaf of groupoids on the category of perfectoid spaces with the V topology. So the V topology is sort of like FPQC. It's a very, very, very fine topology with lots of covers. It has good descent properties, sort of like this FPQC topology. So okay, so you could get one of these V stacks just by taking a perfectoid space and considering the sheaf that it represents by Yoneda. So this category certainly contains all perfectoid spaces. But importantly, it also contains all rigid spaces. There's a way to get from rigid spaces to V stacks. You find a pro-atal cover, which is perfectoid, which can always be done kind of in the way I suggested by taking all of the possible atal covers and kind of taking a limit and letting this X diamond be the, okay, so I've expressed X as a quotient of X tilde. So X tilde is perfectoid, so it gives you a representable sheaf, and you kind of quotient this by the descent datum to X. So you just work only in the world of sheaves on the category of perfectoid spaces, and you get this notion of a diamond. So this X diamond is what's called a diamond. It's like an algebraic space. It's the notion, it's like the analog of algebraic spaces in this world, and it's defined as a quotient of a perfectoid space by a pro-atal equivalence relation. Okay. All right, well, to review, I guess, since I said very much about this stuff, but there's rigid spaces, the things maybe we ultimately care about. You can take a rigid space and diamondify it. Diamonds are way bigger, and they contain like all perfectoid spaces, for instance. And then everything's contained in this huge category of V stacks. And that, in this world, you're allowed to kind of take stacky quotients by stuff. You might be interested in that. So a good example that's going to come up soon is like this sort of quotient. If I have a rigid space X, G is a profinite group acting on it, I'm allowed to take X diamond modulo G. So this is kind of the sheaf theoretic quotient of a representable sheaf by another representable group sheaf, this G. Okay. Any questions now? So we're going to go to the next. Okay, very good. All right, so leaf, Faltings isomorphism. I got 10 minutes, but didn't we start late? All right, a little bit. So all right. Okay, so Tate started it all. So this is, Lubin-Tate space is a really familiar object for a lot of people for very different reasons. So I want to go over it. So let's say we've got a formal group over FP bar, height n and dimension 1. There's only one of these. So up to isomorphism. This has a deformation space, and I'm going to call that deformation space LTN, Lubin-Tate space. So theorem from 1966. Okay, complete description of what this formal scheme is. There's really n parameters. One of them's p, and the rest of them are just formal parameters. And it's a very important theorem. It extends beyond the case of formal groups to like formal OK modules if you have a local field like this. And then in the special case where n equals 1, there's no parameters here. So that means the deformation is unique, extending up to the OK on ramified. And then if you adjoin the torsion in that unique deformation, you get the maximal abelian extension of K. So in the modern way of talking about local class field theory, this is kind of how you construct the maximal abelian extension of a local field. 1965, all right. In general, LTN, it's a formal ball. And this ball, or actually its rigid generic fiber, which we know is this other thing, this other rigid ball, it's really important for local Langlands for the group GLN. So this was key to proving local Langlands for GLN in the proof of Harris and Taylor. So kind of important. But it's important for other reasons. So this now we're I'm going to reference Jacob's talk a little bit more now. So certain rings, you can talk about them having an enhancement in homotopy theory. So there's a commutative ring spectrum. This is called Morava E theory. I'm going to call it just En. Ring spectrum, so it's a cohomology theory valued in rings. You can plug in a topological space to this. If you plug in a point and just take En0, so I should say like a cohomology theory, there's like a degree. So the 0th degree cohomology is this deformation space. Generally, it's something else. Don't worry about it. I don't want to hustle here. So the thing is, what does this have to do with formal groups at all? So it's got this property. If I have a line bundle on a space X, you know how to form the usual churn character. It's valued in the second homology with Z coefficients. With this kind of cohomology theory, this EN cohomology, you also get a churn class. The EN it has this property called complex-oriented, and that basically just means it has a theory of churn classes like this. So the first churn class of a line bundle is an E2. And then it's important to know what happens when you like tensor two line bundles together. What happens to the churn classes? For ordinary churn classes, they just add. But for these churn classes, they add in gamma. Gamma here is the universal deformation. The coefficients of gamma lie in the EN0, and you kind of expand this Paris series out, and that tells you how the churn classes work under under tensor product of line bundles. So it's a really fantastic theory here. And while I'm on the subject, so this is the subject of homotopy theory, and some aspects of homotopy theory are called like brave new algebra because it sounds like we're reinventing, I think that's Waldhausen's term, we're reinventing a lot of very familiar things in a kind of unfamiliar circumstance. So in this world of spectra, there's an initial ring, S, just like Z is the initial ring in usual algebra. So this is called the sphere spectrum. Its homotopy groups are very, very interesting, homotopy groups of spheres. And Z has some prime ideals. Oh no, I just ran out of, wait. No, it's still working. So Z has primes. I mean, it's got the 0 prime. It's got like the generic point. But everyone else is a finite prime, and so these are the residue fields. Well, the residue fields of S are known. They are Morava K theory. And the notation really ought to be Kp comma n. But anyway, for each prime and every n between 0 and infinity inclusive, you get a residue field of S. So that's called Morava K theory. And so the fact that you have all these different n's, I guess each one is supposed to be like a frequency or a color, and that's why this is chromatic homotopy theory. ZP, that's an important object. It's like a completion at Kn. And you can do this completion. So this operation, it's like, I mean, it came up in Dustin's talk. So this is called Bausfeld localization. I hope I spelled that right. And it's basically like the ZP. But now we're completing at one of these kind of odd primes. It's one of these strange primes, this K of n's, yeah. Bausfeld, thank you. Okay, good. There's an I there. All right. OCP, also very interesting. That's like our EN. So the EN was from the previous slide. That was Morava E theory. And then a really other important object, the local Galois group at P. The analog of that is something called the Morava stabilizer group. But to number theorists, it's basically just the automorphism group of the formal group that we fed into this. So this formal group, it's gamma 0. Gn is like automorphisms of the pair, really. So it's an extension of Z hat, that's the Galois group here, by the automorphism group of this thing, which is well known. It's like a division algebra of invariant 1 over n, and you take the units. So the group theory of this thing is pretty well known. So this Gn is sort of like a local Galois group. Yeah. What's not a ring? Well, that's yeah, Gn's a group, yeah. All right. Okay, so I want to take an old theorem of Tate, which I am utterly obsessed with, and move it into this chromatic homotopy theory world. So this theorem is from Tate's p-divisible groups paper. It says that if I look at the cohomology, this is continuous cohomology of the Galois group acting on Cp. So the H0 is Qp, and the H1 is also Qp. So I can write it as a ring like this. This is an isomorphism of commutative graded rings. So this is not a polynomial algebra, really. X has degree 1, so x squared has to be 0. So I just mean this has kind of got degrees 0 and 1. I have never read a paper in more detail than I have read Tate's p-divisible groups paper. I've read, there's individual pages of that paper that are burned into my eyes. I know where each word on the page is. It's that kind of thing, right? I think everyone has a paper like that. Mine is this paper. All right. Our theorem, this is with Bartel, Stapleton, and Schlank, is basically like what the analog of this theorem is for the objects that appeared on the last page. So the Galois group got replaced with this Morava group. The CP got replaced with this, okay, this was a power series ring. It was like the universal deformation ring. But the fact that it's CP, not OCP, means I have to invert P, so I do that. So the theorem says that it's kind of similar, except there's additional generators. So I think the two theorems are an analogy with each other. So the right-hand side is, where did it come from? Well, it came from the continuous cohomology of a certain Lie group, so that was GLN-ZP here. And this whole theorem is relevant to the calculation of the homotopy groups of the K-and localized sphere. So the homotopy groups of the sphere themselves is kind of mysterious, but we're trying to isolate patterns which can be detected after localizing at a particular prime, in this case, K of n. Okay. So now we can actually compute exactly what these homotopy groups all are. Yeah. So I wanted to go into some aspects of the proof of this. There's only 3 slides, so it's going to go over like by 2 minutes. I don't know. So the key to this theorem, and maybe the question of where that group GLN-ZP appears, is in this isomorphism of V stack. So this isomorphism has a very interesting history. Faltings talked about it, but in different language. It was further developed by Farg and also in my paper on p-divisible groups with Schulze. And the modern interpretation, I would say, is that 2 stacks are the same. One of them is LT and eta. That's the rigid ball, diamondified and mod up by a profinite group. On the other side is Drinfeld symmetric space. That's the complement in every QP rational hyperplane inside of projective space. But when n is equal to 2, you get the space I talked about before, the p-adic upper half plane. So get this. The open ball in p-adic geometry is the same as the upper half plane up to the actions of some finite groups. So we've, it's well known in complex geometry, the unit disk is the same as the upper half plane. Well, that's not literally true for us, but it's like true in this sense up to the action of these 2 different groups. Yeah. How does this get applied? Real fast. I mean, since we've got this isomorphism, you have to apply some theorems in integral p-adic Hodge theory. I just want to take the O plus cohomology of both sides. On the one side, you're going to get this group to appear. On the other side, you get this to appear, up to some error terms. But the error terms all end up being p power torsion, so they kind of go away after you invert p. Those torsion terms are kind of arithmetic in nature. They relate to the same torsion terms that Tate considered in his original paper about this. And so the result of this is that the cohomology of Gn in this kind of terrible ring, this action is really hard to describe, is sort of way, way, way simpler. This is an isomorphism after you invert p. That's another formulation of the same theorem. Oof. Okay, where did this isomorphism come from? This is the last slide. So another description of this stack. So I could write it this way. It's like you have the stack of formal groups, and it's got a height and locus in the p equals 0. There's a p equals 0 locus, and then within that, you have a locally closed subspace of just height and formal groups. Complete along that, and you get exactly what the stack is. I don't want to say that's tautological or anything, but it's not as deep as some of these other statements are. So I just want to explain what this isomorphism is over C points. So what's a C point? So C is going to be algebraically closed. What's a C point of this stack? It's going to be a p-divisible group G over OC of height n and dimension 1. I mod it out by Gn, so that means I'm not deforming anything. If I didn't mod out, I would have to say, oh yeah, the special fiber of this thing has been identified with something in characteristic P. And then to this, there's an associated sequence. We now call it the Hodge-Tate sequence, but it's in Tate's 1966 paper. Here it is. Let's just focus on this first thing. It's something like a Hodge. It's something like a Hodge filtration. This is like singular homology. And this is something like differential forms, although it's been dualized. So it's a Lie algebra that appears here. So it still exists. So what does G determine? You get a free ZP module T, that's this thing, together with a one-dimensional subspace of it tensored with C. If you really think about it, that's exactly what this quotient is doing. You get a, if you have a, this thing is telling you all the different ways to construct a rank n free module, and then once you've trivialized it, a line inside of it, it lives in Pn minus 1. This part is kind of tautological. So now we've landed in Pn minus 1 modulo GLNZP, and conversely, a point of this, you can go the other way. You can start with a point of this. It determines a p-divisible group over OC, but not necessarily the sort you started with. It only comes from a connected group, that is a formal group, when the point lies in this locus. You have to throw away all of the all points on all rational subspaces of this to get this result. Oh, that's my last slide. So I just want to say, spend a special thank you to the organizers of this incredible conference. Let's thank them too.